Hello, my name is Antoine from the Technical University of Darmstadt and the Medical and Environmental Computing Group. And today I will be presenting our work on how reliable out-of-distribution generalization methods are for medical image segmentation. And so today I will be talking to you about why out-of-distribution generalization is important, what it is, what are the different methods to tackle this issue, and finally I will be presenting our results. So first off, why is out-of-distribution generalization important? While semantic segmentation is a crucial step in many clinical procedures, however, it's also quite time-consuming. And insufficient generalization may limit the implementation of automated solutions in practical applications. And there is one application which retained our attention, and that is hippocampus segmentation. Indeed, various diseases like Alzheimer's disease, schizophrenia may alter the shape of the organ. The age of the patient may also be a factor. And for instance, if we look at the plot on the right, we can see the hippocampus volume distribution in the heartbeat dataset, and we can clearly observe a distribution shift depending on the diagnosis. And so this is typically something that can hinder the generalization of a model. So now if we formalize the problem definition, we can consider that we have gathered a certain number of datasets under different training environments. And so one environment simply encompasses the different parameters for your acquisition. That is, which hardware you use, which acquisition parameters, and so on. And so if these parameters change, you get a different environment. And as usual, the data points of one dataset are identically and independently distributed. And so these training environments are, of course, part of a large set of unseen but related environments. And our goal is to use this training data to learn a predictor which will minimize the risk on unseen data. The risk for one environment is simply defined as the expected loss for the predictions on this environment. And so, having said that, the first family of methods which tackle this issue is regularization-based, and usually takes the form of a loss function where you will minimize your empirical risk as usual, but you will also find a regularizer which will enforce an intuition across all training environments. For instance, here with the Verax loss, we can see that the regularizer takes the form of the variance across risk across all training datasets. And so this is something that you might want to minimize simply to ensure that your model will perform as well on each and every training dataset. To give another example, the IRMV1 loss will enforce the optimality of the predictor on each training dataset. And so this is the kind of method which you will find in this family. In contrast, the second family uses domain prediction to find a harmonized data representation. And so it uses an architecture which is composed of 3 different parts. An encoder which will find a new data representation, a segmenter which will solve the main task of segmenting the input, and a domain predictor which will solve a secondary task of predicting from which dataset an input comes from given the new data representation. And the intuition here is that if the domain predictor does no better than random guessing, then there must be no information left in the new data representation regarding the source of the input. And as such, you have found a harmonized data representation. And the major strength of this approach is that you do not need any labels to find a harmonized data representation, as it does not involve the segmenter at all, and for each image you know from which dataset it comes from. So that's perfect for so this method is perfect for semi-supervised training. So now in our work, we also decided to introduce a combined method where we use the domain prediction architecture, but we also use the Virax loss on the segmental to help the model learn robust features on labeled data, while also retaining the ability to train on unlabeled data. So to compare these methods, we gathered a corpus of 3 publicly available datasets for hippocampus segmentation. We nicknamed these datasets Decath, Harpy, and Dryad. You can find the references on the right. And as you can see, these datasets all represent a different training environment, as we find a distribution shift in patient's age from one dataset to the other. There is also a distribution shift in diagnosis from one dataset to the other. And so we expect these different factors to somewhat hinder a model from generalizing from one model to the from one dataset to the other. And so this is exactly the first thing that we checked. And so here we trained 3 models using the standard approach on their respective datasets. And so if we take a look at the diagonal, we can see the results for the model's respective training dataset. So all these dice scores are close to 85%, so that's almost state of the art. But what is much more interesting is that if we take a look at the first row, we can see that the model trained on Decath completely fails to generalize on the Harpy and Dryad datasets. In contrast, the model trained on Harpy already generalizes quite well, and the model trained on Dryad reaches some middle ground. And so here we can clearly see that the distribution shifts found from one dataset to the other may vastly limit the ability of a model to generalize to out-of-distribution data. And so now that we have this reference frame, we decided to compare the 4 methods in a fully supervised setting. So we compared a standard unit, a unit using the Virax loss, a standard domain prediction method, and finally the combined method. And so here what we do is that we train each model on 2 datasets, and then we evaluate them on the out-of-distribution dataset. So in this first setup, the models are trained on Decath and Harpy. And so if we take a look at the results for these 2 columns, we can see that all methods perform almost as well as one another. There is no clear outlier here. And if we take a look at the column for the Dryad dataset, so this is the out-of-distribution dataset, we can see that all out-of-distribution generalization methods have an edge over the standard approach, with our combined method being ahead slightly. If we take a look at the last column, we can see the domain prediction accuracy. As a reminder, if this accuracy is close to 50%, it's close to random guessing, and if it is the case, then we all information related to the source of an input has been removed from the new data representation. And as you can see, this accuracy is quite close to random guessing, but not quite equal. And so we can conclude that most information related to the source of an input has been removed, and the new data representation has been harmonized. If we now take a look at the second setup, we can see that the models were trained on the Decath and Dryad datasets. So once again, the results for these 2 datasets are really close one another method-wise. And what really interests us here are the results for the Harpy dataset, which is the out-of-distribution dataset. So once again, the out-of-distribution generalization methods have an edge on the standard approach. This time the Virax loss performs better than the other methods, although the other 2 are closely behind. And in the last setup, we have trained our models on Harpy and Dryad. The same comment can be said as before for the training for the results on the training datasets. And the results on the Decath dataset are much more interesting. So we can see that the unit plus Virax method clearly outperforms all other three methods. The domain prediction method clearly also shows the advantage of finding a harmonized data representation, as it has a higher mean die-score and also a much lower variance than the standard method. Here, the combined method completely fails to generalize despite good results on the training datasets. And what is quite interesting here is that the domain prediction accuracy is still near random guessing, but this clearly shows that the domain prediction accuracy cannot be used as a metric to guarantee that a model will generalize well to out-of-distribution data. And so, having seen this result, we decided to investigate further and to try and plot predictions from two models from two different folds of a 5-fold cross-validation. So in this last experiment using the combined method. And so if we take a look at the predictions on the right, we can see that we have a first robust model which reaches a die-score of 85% for this prediction. And we can clearly see that the segmentation nicely captures the shape of the organ with also minimal noise, while the second model completely fails to predict a proper hippocampus. There is also a lot of noise. But what was really interesting is that these two models reach almost the same die-score on the validation data. It was even within 0.1% from one another. So if we were only to look at the metrics for validation data, we wouldn't be able to tell one model from the other. And so what we can conclude here is that unless we try to predict using a model on unseen data, you will not be able to be sure that the model will be able to generalize. And so we tried out semi-supervised training. So this was also the perfect setup to see if domain prediction methods were able to get an edge from training on unlabeled data. And so in this first setup, we used Harpy and Riyadh as two fully labeled datasets. And we also used the Decath dataset. However, we only used 10 labeled data points, which were split equally between training and validation. And what can be said here is that the standard approach does really well here. It's even slightly better than the other three methods. We also noticed that the domain prediction-based methods became somewhat harder to tune here. And as you can see, the domain prediction accuracy is far from random guessing, which would have been 33% accuracy. And so to try and push the semi-supervised setup, we decided to use as few labeled data points as possible from each dataset. So here we used only 10 data points for each dataset, and the same comments can be made as for the first experiment here. So to conclude, in our work, we propose a careful comparison of out-of-distribution generalization methods. The Virax loss also shows promising results, and augmenting the Virax loss with domain prediction may be beneficial. In the future, we would like to investigate further how these two strategies can be combined. And so I thank you for your attention. If you have any question, feel free to contact me.